I'm going to do the video a little bit differently this time because I went through the assignment and discovered that there's really not that much calculation to do. There's not a lot of reason for me to write down a bunch of equations. So I'm just going to go through and look at the assignment. And you can go along with me. I'm going to talk about all of the answers to these questions. So here I am, homework number 24, the Work-Energy Theorem, the first question, all work and no play. Here on the left-hand side, it gives me an actual lesson on calculating work. The real critical thing here, the important point that goes through most of this homework assignment, is that in order to calculate the work done by the force, I have to discover the component of the force that is in the direction of the displacement or opposite the direction of the displacement. Forces and their components that are perpendicular to the displacement do no work, and that's a critical idea to have. Forces that are in the direction of the displacement do positive work. Forces that are opposite the direction of the displacement do negative work. So with those simple ideas in mind, I should be able to power through this whole homework assignment very quickly. So here we go. I have this diagram down here on the lower left with a bunch of forces pointing around all over the place. And what happens is, because of all these forces, however it works out, this orange object here goes to the right. It goes specifically in this direction, and that's important because in order to calculate work, I need to know the displacement. The displacement is represented by this blue arrow down here, and it's called S. Now, some people use S for displacement. We know that in one-dimensional on the x-axis, we use delta x for the displacement. Here, the writers of this problem choose to use S. At any rate, the object displaces to the right. So what can be said about the sign of the work done by the force F1? Well, here's the force F1. It's the one on the top here. It points upward. When the displacement is to the right, that means that the force F1 is perpendicular to the displacement, and therefore it does no work. So I suppose I would answer it is 0 because there's no work done. What can be said about the work done by the force F2? Well, F2 generally points in the direction of the displacement. That is, F2 has a component that points to the right. Because the component of F2 is in the direction of the displacement, it does positive work. If I look at F3, F3 points in the opposite direction from the displacement. F3 points to the left, the displacement is to the right, and so the work done by F3 would be negative. The work done by F4, where's F4? F4 is completely in the direction of the displacement, and so it does positive work. Force F5 is sort of generally opposite the direction of the displacement. The displacement is to the right, and F5 has a component that is to the left, and so the sign of the work done by F5 is negative. Work done by F6, once again, F6 points downward when the displacement is to the right, and therefore F6 does no work at all. F7 has a component that is generally in the direction of the displacement, and so it does positive work. So you see, once you have this idea in your head, it's very easy to go through and name how these things should work out. In the next series of questions, we want to use a formula to calculate. Well, part H has a new diagram, I think. It's talking about the 18 Newton force. You see here, it's one of two on these diagrams. I switch to the next diagram and I see the 18 Newton force. How much work is done by it? Well, the displacement, once again, is to the right, and the 18 Newton force is completely to the right. The angle between that force and the displacement is 0. It's going in the direction. So all I need to do is simply multiply 18 by the displacement. So the answer is going to be 18 times 160. For part I here, this 30 Newton force is a little bit more complicated because the 30 Newton force has two components. It has a component that is in the direction of the displacement, and it has a component that is perpendicular to the displacement. The perpendicular component does no work. The work is done by 30 cosine 30. I know that I'm using cosine to find that horizontal component because that component is the component that is adjacent to the angle, and I always use cosine to find the adjacent component. So what I have to do here is take 30 times the cosine of 30 and multiply by the displacement 160 to get the work done by the 30 Newton force. Work done by the 12 Newton force? Well, the 12 Newton force points exactly the opposite the direction of the displacement. So the work done by this force is easy to calculate. It's the force, 12 newtons, multiplied by the displacement, 160. Little caveat. The 12 Newton force points opposite the direction of the displacement, and so it does negative work. The way that comes out in the math is technically it's 12 newtons times 160 meters times the cosine of the angle between them. Well, the angle between the 12 Newton force and the 160 meter displacement is 180 degrees. The cosine of 180 degrees is -1. So if you want your negative sign to come from mathematics, that's where it is in the calculation. And then we want for the 15 Newton force. Once again, this work is going to turn out to be negative because the 15 Newton force generally points opposite the direction of the displacement, so we'll do negative work. But I can't use the 15 newtons. I need to use the component that is parallel to the displacement, or anti-parallel in this case. So I want the horizontal component of the 15 Newton force. Once again, I'm going to use cosine 15 newtons, cosine 40 degrees. And that'll get me the component of the 15 Newton force that points opposite the direction of the displacement. So 15 cosine 40 times 160, and that work is negative. If you want to be super mathy about it, you can go ahead and say that the angle between the force and the displacement is 120 degrees. If you put that into your calculator, the cosine of 180 degrees is going to give you the negative of the cosine of 40 degrees. And so the math works out just fine. So I can move on to the next question now. That was a whole lot to do in that first question. It was mainly ideas, and those ideas are going to carry on. So here I am in question 2. Words, all over the place, but I know what I'm doing. Part A. Which of the following statements accurately describes the sign of the work done on the block by the force of the push? Well, here's my diagram. The push is in the direction the block is going. So it's going to do positive work in general. What accurately describes the sign of the work done by the normal force? The normal force is perpendicular to the displacement. It does no work. Which describes the sign of the work done on the box by the force of kinetic friction? There's the kinetic friction there. It points opposite the displacement. It does negative work. You get the hang of this? It's fairly obvious. Which of the following statements accurately describes the sign of the work done on the box by the force of gravity? Here's the force of gravity, labeled as the weight. The force of gravity is perpendicular to the displacement. It does no work. Now, what are you doing in your bedroom? You've got a dresser on the carpet. Is this a second diagram? Part E? No, that's an incline. So you've just moved into your new apartment and you're trying to arrange your bedroom. You would like to move your dresser, which has a weight of 3,500 newtons, across the carpet to a spot 5 meters away on the opposite wall. Hoping to just slide your dresser easily across the floor, you do not empty your clothes out of the drawers before trying to move it. You push with all of your might but cannot move the dresser before coming completely exhausted. How much work did you do? You didn't do any work! How can there be work if there's no displacement? You push on this dresser, you push, nothing happens. They're trying to trick you a little bit there because you get tired while you're pushing on the thing. So you might say that you expended some energy while doing it. Something happened. Well, what happened was biochemical. It's inside of your muscles. In order to create a muscular contraction to exert the force, your muscles have little protein molecules in them which attach themselves with electrodynamic forces and contract. That's where the work is done that exhausts you. But still, this dresser didn't move. And so therefore, the work done on the dresser is 0. Now part F shows me figure 2, so I'll quick switch over to figure 2. It's on an incline. Box of mass M sliding down a frictionless plane, inclined at an angle phi, that's the Greek letter phi, above the horizontal as shown in the figure. What is the work done on the box by the force of gravity W if the box moves a distance d? Well, the component, the weight force on this box, I know my inclined plane free body diagram, has 2 components. It has a component mg cosine theta, which is perpendicular to the incline, and therefore does no work. But it has a component mg sine phi, which does do work because it points parallel to the incline. So all I have to do is take mg sine phi and multiply by the displacement d down the incline. So I look at these answers and what W, D, well, first of all, in our physics, we don't use W for weight. Right here, using W is silly because there's work is equal to, and there's another W in it. That's strange. So that lowercase w is mg. And I've got an option of 0. Well, that's not true. And I've got these two weird, I've got the cosine option. That's not true because the cosine component of the weight does no work. So I think maybe it's this one. Well, you have to understand something, a little bit something from your math. And that is that the cosine of 90 minus phi is equal to the sine of phi. So it turns out that this second one is in fact the answer, having a little bit more to do with math than anything else. The planet Earth travels in a circular orbit at a constant speed around the sun. What is the net work done on the Earth by the gravitational attraction between it and the sun in one complete orbit? Assume with the blah blah with the blah blah blah. There are equations as the answers. It doesn't matter because the work done is 0. And the reason why is when an object goes around in circular motion, the force that causes that circular motion, the centripetal force, is perpendicular to the direction of travel of the object. Therefore, it's perpendicular to the displacement. Perpendicular forces do no work. And that really makes sense here because if the sun did work on the Earth, as the Earth traveled around the sun, the Earth would go faster and 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 faster. And after 5 billion years of that, we'd be going pretty damn fast. A block of mass m pushed up against a spring with a spring constant k until the spring has been compressed a distance x from its equilibrium. What is the work done on the block by the spring? Well, I learned about this, that the work done by the spring is the negative of the change of the spring's potential energy. Spring potential energy is 1/2 kx squared, and that answer does not appear here. And so my answer is none of these. Woo, man, this is exhausting. Oh, I hit next. Am I going to get graded? No, I'm all right. Question number 3. Okay, now we got some calculations to do. Boy flies a kite with a string at a 30-degree angle to the horizontal. The tension in the string is 4.5 newtons. I made a little diagram of this. So here's the boy standing here, and here's the string attached to the kite, and there's some tension. And I didn't draw the angle in, I should have, but the angle theta would be right there. So this force that the kid is exerting on the kite and the kite is exerting on the kid is an action-reaction pair via Newton's third law, has a component t cosine theta in the horizontal direction and a component t sine theta in the vertical direction. So this is what I should be visualizing. We will come back to this diagram in just a second. How much work does the string do on the buoy if the buoy stands still? There's no displacement, and if there's no displacement, there's no work done. Easily answered. How much work does the string do on the buoy if the buoy walks a horizontal distance of 11 meters away from the kite? Well, now I need to go back to my diagram. As the buoy moves, here's the buoy right here, as he moves to the left, the kite is pulling him to the right. So the kite is going to do negative work on the buoy. Don't worry about the t sine theta component. That component is perpendicular to the displacement and therefore does no work. So the work done in this case is going to be t cosine theta, and I'm given the tension and the angle in the problem statement. It's going to be t cosine theta multiplied by the displacement, which for me is 11 meters, and then I know that that work is negative, so I'll enter it in as a negative number of joules. How much work does the string do on the buoy if he walks the same distance toward the kite? Well, it's going to be the same work, except this time the force of the kite, t cosine theta, is in the direction the buoy is traveling, and so that t cosine theta will do positive work, so it'll be t cosine theta times 11. A little bit of slow internet. Question number 4. Okay, so I've got a book is lying on a table that is 0.74 meters high. If I pick up the book and place it on a bookshelf at 2.2 meters above the floor, during this process, how much work does gravity do on the book? Well, the work done by gravity is going to be mgh. I demonstrated that in a lecture. It's mgh, it's mgh, it's mgh, it's mgh. But you have to be careful here, because the mgh, where am I going to measure the height from? Well, I'm going to measure it from the top of the table, but it tells me the top of the table is 0.7 meters off the floor. So what I have to do here is calculate mgh, but for the height, I'm going to use the 22 meters, the 2.2 meters of the bookshelf minus the 0.74 of the table to get the height right, to calculate that. And that, of course, will be the work done in joules. During this process, and that work done by gravity, by the way, is negative. It's really important, part A, that work done by gravity is negative, because as I lift the book up, the displacement is upward, but the force of gravity is downward. Since the force of gravity is opposite the displacement, the work done is negative. During the process, my hand does the same amount of work in the opposite direction. That is, I do as much positive work lifting the book as gravity does resisting the lifting of the book. The reason why is that when you take the total work at the end, the positive work done by me and the negative work done by gravity, the total work done is equal to 0. And that makes sense, because the book has no kinetic energy to start and no kinetic energy at the finish. That is, the change in kinetic energy of the book is equal to 0. And so the total work is equal to 0. Positive work done by me, negative work done by gravity. Question 5. 2 ropes, bird's eye view right here. So I'm looking at this from above. I'm pulling this thing to the right, and there's some friction force that opposes that. This is looking from above here. The 2 ropes shown in bird's eye view of figure 1 are used to drag the crate 6 meters across the floor. How much work is done by the kinetic friction force? Well, now I'm getting to be old hat at this. The friction force is exactly opposite the direction of the motion, so it's going to do negative work. It's 500 newtons of force for 6 meters. Negative work in joules. How much work is done by T1? Well, you see I'm going to have to take a component here. I want the component of T1 only in the direction of the displacement. The displacement is to the right. So what I want is 326 cosine 20 multiplied by 6 meters. That is the work done by T1 in joules. How much work done by T2? Same thing. 223 newtons cosine 30 degrees to get the component of the tension that's in the direction of the displacement, and multiply by the displacement of 6 meters. 223 cosine 30 times 6, a positive work done in joules. There's a fun one. 27-gram plastic ball is moving to the left at 23 meters per second. How much work must be done to cause it to move to the right to 23 meters per second? Oh my goodness, I have to calculate and see if the kinetic energy is 1/2. Oh, wait a second. The work done is 0. The reason why is that the work-energy theorem tells me that the work done is equal to the change in the kinetic energy. Kinetic energy is not a vector. Kinetic energy is not a vector. So kinetic energy to the left and kinetic energy to the right are the same thing. So for this plastic ball, the initial kinetic energy and the final kinetic energy are equal to each other. And so the change in kinetic energy is equal to 0, which means the work done must be equal to 0. And you say, well, Dad, I don't understand, because you see, you have to exert a force on it, and forces do work. Well, listen. So the thing is moving to the left. In order to stop it, I have to exert a force to the right and do negative work. So I do negative work, and then I bring it all the way to rest. But now, to get it going in the opposite direction, I have to do exactly the same amount of positive work to get it going in the opposite direction. So yes, I do work during the process, but the total work that I do is equal to 0. Very often, physics problems, particularly in the realm of conservation of energy, are more about thinking than they are about calculating. And sometimes students struggle with that, because we learn in math class, you figure out which equation you use, you plug the numbers in, you get your answers, and off you go. Physics isn't math. It's understanding the nature of the universe, which happens to express itself mathematically. I can't help that. But very often the problems that we solve involve a little bit of careful thinking before calculating.
Mm-hmm.